Hello Adrian, this is Jim Starrett from Summit Custom Spray Drying here in our Flemington, New Jersey location. And we're standing in the pilot laboratory room that we have. A direct fire thermal oxidizer is connected to the system. I'm providing this video just to give you an idea of how we did our system, set it up according to airflows, and we'll show you upstairs the thermal oxidizer in operation. The purpose is just to give you instructions about maybe moving forward with a system for your dryer number 1 out there in the Tonebridge location. Basically, we have just a small pilot laboratory dryer. This is a older Mullen engineering system that we picked up. A spray dryer system here that basically houses airflow to the thermal oxidizer. We also have ventilation from the ceilings that pull in just to evacuate the room air. The volume of airflow that exits from the spray dryer is basically about 425 meters cubed per hour out of this system. And then we bring in an additional airflow through the ventilation for the room at about 2,550 meters cubed per hour. There are 2 pickup point locations using a common exhaust fan, and there is a dedicated fan on the dryer system that converges into the main ductwork before it goes into the thermal oxidizer. This is our main control panel that operates the system. It actually houses not only the thermal oxidizer controls, but also the laboratory inside here. So typically a control panel for the thermal oxidizer standalone would not require a panel as large as this one here. So basically, this is the control panel that controls both the dryer and the thermal oxidizer. With what you can see inside here is an Allen Bradley PLC Slick 503 with dual burner controllers, one for the dryer and one for the thermal oxidizer. This is the operating interface machine, which basically we put in touchscreen controls. It gives us a little more flexibility because we do have a PLC here. And then down below is a digital chart recorder, which records full-time data onto micro disc, and we can keep those in for multiple years of recordings. Our regulations only require a single chamber temperature monitoring. We do not have to monitor our inlet or outlet. So basically our controls here, we can identify and start up certain portions of the unit, and this is primarily for the dryer system in here, where we can control dampers, the fan speeds, scrubber pumps, lubricator, and then we also have the oxidizer, which is a relatively simple start-stop system, and we have a separate oxidizer fan for that as well. The overview screen identifies the pilot lab system going into a small collection, and then a wet gas Venturi scrubber, and then it comes into a small fan that pushes it into the main fan of the system, in which all the airflow is housed through the thermal oxidizer, and we'll show this to you when it's in operation. Okay. On the oxidizer, we do have a static pressure control that we can set a variable set points, and then control the speed and the static pressure entering into the thermal oxidizer. This one is also the temperature PID, in which all the airflow is housed through the thermal oxidizer, and we'll show this to you when it's in operation. Okay. On the oxidizer, we do have a static pressure control that we can set a variable set points, and then control the speed and the static pressure entering into the thermal oxidizer. This one is also the temperature PID. The burner system is a nozzle mix burner, so we actually induce all of the combustion air as a source from the process, meaning 100% of it is actually used in the combustion of the burner system itself. This brings the operating temperatures at some point up to about 1530 degrees Celsius exiting the burner, which allows us to operate the actual oxidizer at a reduced temperature somewhere around 480 degrees Celsius up to maybe 593. For us, that's about 900 to 1100 degrees Fahrenheit. Standing upstairs, this is directly above our pilot dryer system down below. And this is actually the main fan for the pilot dryer. Again, it's only moving about 350 cubic meters per hour. So it's a relatively small system. You can see it comes up from the floor, down through the venturi, and then in the fan. Now, if you'll notice, this is the primary duct that is moving the ventilation from the room. And the room air exiting is about 2,550 cubic meters per hour. So that's in the primary trunk here. And what you notice is that we use a duckbill connection on our process fan. And what this does is this provides minimum interference in case the airflows are varied. It allows the static pressure from the main fan of the dryer to maintain a constant velocity, which allows a more stable operation inside of it. In these direct fire thermal oxidizers, it's not as critical because there are no cyclic valves, but even the room air varying a little bit can cause some changes in the pressure that the dryer may see. So this is the primary exhaust fan that takes the combined airflow from the dryer and the ventilation from the room. This is the inlet side, which is an induced fan, and this is what provides the positive combustion air into the burner system itself. So the discharge of the forced air blower now becomes positive combustion air for the burner oven pack. This is a small, probably 4 million BTU burner system. And again, 100% of the process combustion air is forced into this medium velocity nozzle mix burner. And again, we're requiring temperatures as high as 2,800 to 3,200 degrees Fahrenheit through the discharge of this particular burner system. So this is our equivalent of an IRI gas train. It is a small DUNGS unit, which hopefully you have a DUNGS unit as well, or some self-checking system up to European standards that could be integrated. And it's very simple block and bleed system with a 4 to 20 milliamp control valve. This is all that is needed to regulate and control the temperature of the thermal oxidizer. The system comes in and we've got two thermocouples located on top. They're only about 24 inches apart from each other. The thermal welds are only about 24 inches apart from each other, and they're only about 4 feet from the discharge of the burner. But that's okay because all the airflow has to pass across both of those before it makes a 90-degree turn and exits up through a triple wall exhaust stack. And this is so that as it vents through the building, the actual exterior walls of the stack are actually relatively cool because we do have direct heat exiting this particular unit here. The physical dimensions of it are relatively small, with about 7 feet or about 2.2 meters by about 5 feet, so about 1.8 meters tall. And then the length of it, the maximum length is up to 3 meters long to the back end before it makes a transition and travels up through the stack. The stack actually allows more retention time, so all that was calculated into the volume of air to give us a minimum of 2 seconds of residence time through the system. Okay, we're going to go ahead and start the system up, and what I want to do is basically show you what the flame may look like under operation. So basically I'll have to start both the dryer fan and also the thermal oxidizer fan and adjust the speeds accordingly. And as we ramp up to speed, we'll get into a condition where we can purge the burner and then ignite it. Here you see the system is fired up, and you can see it's a relatively small flame from the burner right now. We're going to try and open it up a little bit. point adjustment. We're only at about 250 degrees Celsius. You can see now again all the process air runs through it, brings it up to temperature, and then it cuts back a little bit. But again, we've never had an issue to run it much beyond our 900 or 1100 degrees Fahrenheit in our history. And this is the modulating gas valve. Very minimal operation on it, very stable. Just occupies the temperature, and then it holds the set point very well. Again, according to the dual thermocouples located on the unit. Set point. Right now you can see the temperature is at 660. We're going to readjust it to about 750. And you'll see that the gas valve controls, activate the output on the 4 to 20, taking the set point back up, and now the temperature should climb right back up, which is the red line, if you can see that on the system. And it'll take it up to the operating set point, and basically once it hits the 750, it'll start cutting back on the gas valve again. So it gets there very quickly, and there's overshoot. You'll see it'll stabilize out and stay right on that 750 mark. So that's basically the operation of the system.